Okay, now it's time to look at some examples with torque. And this first example should look very familiar to you, or at least the first part of the question. A 5-meter long, 30-kilogram seesaw has adjustable seats that can be slid forward or backward to accommodate different users. It's pivoted about its center of mass. 25 kilograms child sits at one end of the seesaw. Where must a 500 Newton force be applied in order to hold the seesaw with the child horizontal in the air? This is very similar to the last example that we did on the last video, but we'll go through it anyways just as a refresher. I'm going to draw a picture. Here's our seesaw. It's pivoted at its center, so right about there. And let's see, we know that there is a 25 kilogram child on one end. Let's put him there. 25 kg. And we want to know where we would put a 500 Newton force to hold the seesaw with the child horizontal in the air. Obviously, it's got to be somewhere over here, but we want to know exactly where. Well, we've come this far, and now we should really be thinking, okay, we really need to put the forces on our picture here, okay? We need to draw a free body diagram, but we're not just going to reduce it down to a dot, we're going to draw in the forces where they actually act. And actually, before I even do that, I should pick an axis of rotation. I'm told that we're holding the seesaw horizontal. That tells me that this object is going to be in rotational equilibrium. There's not going to be a net torque. If that's the case, we can set our axis of rotation to be anywhere that we want. So actually, let's draw our forces in, and then let's pick an axis of rotation. I know that there's going to be a force from this 25 kilogram box, and that's really being caused by the weight of this object. So I'm going to call this FG1. I know that the pivot point, the fulcrum, is exerting a force upward on the seesaw. That's the normal force. I also know, if this is the center of mass of the board, and I'm told the mass of it, I know that there is a force downward due to the force of gravity on the board. I'm going to call that FGB. And I don't know where this other force is going to go, but I have a good idea it's going to be somewhere on the right-hand side. I'm just going to put a little dotted arrow in, and I'm going to call this F. Before I write my net force equations, or net torque equations in this case, what I really should do is I should think about where to put the axis of rotation. It's going to be pretty easy for me to calculate FG1 because I know the mass of the child. It's going to be easy for me to calculate FGB because I know the mass of the board, and I already know the size of F. What I don't know right now, without doing more calculations, is the size of the normal force. Now, if you are smart, you will set up your free body diagram or your axis of rotation on your free body diagram so that any torques that you don't know or would have to do a lot of work to calculate cancel out. I'm going to put my axis of rotation right at the pivot point because then this force acts right at the axis of rotation. R will be 0. The torque from the normal force will be 0. Oh, and I'm going to put an axis on here. X, Y, plus, and we're going to do our normal convention of counterclockwise is positive. Now, last time we wrote out a net torque equation, just jumped right in. I'm going to show you a different way to do this. We're going to calculate each individual torque before we get to the net torque. Sometimes people like doing that. Sometimes people like writing out the equation and plugging everything into the equation. I'm just going to show you both options. Let's start with the easy ones. We know that a torque is equal to the displacement from the axis of rotation to where the torque acts multiplied by the magnitude of the force times sine of theta, with theta being the angle between R and F if they're written tail to tail. So if we want the torque from the normal force, that's tau n, n for normal force, that's going to be Rn times Fn times sine theta n. We already got done saying that the displacement from the axis of rotation to where the force acts is 0. Therefore, that's 0. The normal force provides no torque. Remember, the units of torque are Nm. For the torque from the board itself, the weight of the board, we have something similar. Rb times Fb times sine theta b. Since the weight of the board acts right at the axis of rotation at the center of mass, which is where we put the axis of rotation, this again is 0. Does not matter what the weight of the board is, does not matter what the angle is. Since that's 0, everything times it is also going to be 0. Tau b equals 0 Newton meters. So we're left with two torques to calculate, the torque from the child and the torque from the force that is holding him steady. Let's see, where are we going to calculate these? Okay. So I've got the torque from Fg1 equals R1, Fg1 sine theta 1. Since our axis of rotation is right here, the board is 5 meters long, the axis of rotation is right in the middle at the center of mass. This distance, this displacement must be 2.5 meters times, let's calculate Fg1. Let's do that off to the side here. Fg1 equals m1 times g. This is going to go real quick. Let's see, it's a 25 kilogram child times 10 meters per second squared. Fg1 equals 250 newtons times, let's see, sine theta 1. R would be straight out this way. F is down. If I draw those together, tail to tail, it's a 90-degree angle between them. Therefore, this is 1. The torque from the child is 625 Newton meters. And the torque from F would be RF times F times sine theta F. Let's assume that the force is going to be straight downwards. Therefore, the displacement vector R is going to be exactly out to the right. F is straight down. It's a 90-degree angle. That's going to be 1. We don't know exactly what RF is, but we can at least plug in that the force is going to be 500 newtons. So we get 500 times RF. Now, we're finally ready to go and figure out what the net torque is. Remember, the net torque is a lot like the net force. We're going to think about what direction the torques would try to rotate the object. The torque from Fg1 would tend to make the board rotate this way. That's counterclockwise. That will be positive. The torque from F would tend to make the board rotate clockwise. That will be negative. And any net torque is equal to I alpha. Remember, we already canceled out the torques from the normal force and the weight of the board. Since we're just trying to balance the board, that means that there is going to be no rotational acceleration or angular acceleration. So this is 0. So guess what? Tau 1 must equal tau F. The torques must be equal to each other. Tau 1 is 625 Newton meters. Tau F is 500 times RF. We simply solve for RF. 625 divided by 500, and we get 1.25 meters. Now, that's the placement of F. What does that tell us? 1.25 meters from what? Remember, R stands for from the axis of rotation. From axis of rotation. Or, if it's 1.25 meters from the axis of rotation on this side, we could also say, let's see, if that's 2.5 and this is another 1.25, 3.75 meters from the left edge. And that's not a bad thing to know because we could move, if we wanted, the axis of rotation around. And as a matter of fact, we're going to do that in the next part of this problem. We're going to move the axis of rotation around a little bit. Okay? So there's a basic rundown of how to use torques to figure out where to put this force. Now, what is the normal force in this situation? There are two different ways to go about this. Okay? One of them is actually just to do a net force analysis. Very simple. You now know the size of each of the forces, or you knew that before, and you can use that to calculate Fn. Think about if we just did a real quick F net y equation. The upward force is the normal force, based on our axis, minus, because all these forces are downward, Fg1, minus Fgb, and then minus F. And that's equal to MAY. I should say MBAY, since it's the mass of the board. Now, this board is not rotating, it's also not accelerating downwards, okay? The center of mass of the board is not accelerating downwards or upwards. It's staying stationary. Therefore, this board is not only in rotational equilibrium, it's also in translational equilibrium. So we're going to say that the acceleration is 0, and therefore, the normal force equals just the sum of all these different forces. The only one we haven't calculated yet is Fgb. I'm just going to do that off to the side here. Fgb equals the mass of the board times g. The mass of the board is 30 kilograms. times 10 meters per second squared. FGB is 300 newtons. So the normal force must be, let's see, FG1 was 250 newtons, plus FGB is 300 newtons, plus F was 500 newtons. Fn is 250 plus 300 plus 500, 1,050 newtons. Just because we're on a torque unit does not mean you're allowed to forget about forces, okay? That's probably the easy way to do this. You could also, if you forgot about that, figure this out using the net torque equation. Now, to find the normal force, the problem before was that the normal force, the torque from the normal force was getting canceled out because our axis of rotation was right there. We can move the axis of rotation around because the object is in rotational equilibrium. Since object in rotational equilibrium can move the axis of rotation. We can move that around a little bit. So what we're going to do is we're going to set it at that left edge. Now, not only can we move the axis of rotation around, but think about what that's going to do to the torques. We're now changing the distance that some of these forces are acting from the axis of rotation, from where we set the axis of rotation. So the size of those torques is going to change. This time, I'm just going to go right into it. I'm going to write tau net equals, if the axis of rotation is over here, guess what? FG1 is not going to produce a torque anymore. Okay? I'll write it in, but I'm going to cross it off immediately. That now produces no torque because that force is acting at the axis of rotation. R must be 0. If we look at our other forces, Fn, the normal force, if the axis is over here, that would tend to rotate things counterclockwise. So I'm going to have tau from the normal force. FGB would tend to rotate things clockwise, so minus tau b. And then this would do the same. It would tend to rotate things clockwise, so minus tau f equals I alpha. But once again, this is in rotational equilibrium. That must be 0. Therefore, the torque from the normal force must be equal to the sum of the torques from the board and from the force. Okay, so now I've expanded this equation out so that I have all my variables included. I know that any torque can be calculated using R times F times sine theta. I know that each of these forces is perpendicular to the R vector, to the displacement vector from the axis of rotation out to where the force acts. So guess what? All of these are 1. And I know the size of all of these forces, except for the normal force. Well, I do know the normal force, but I can calculate what the size of the normal force is. And I know the distance or the displacement away that all of them act. Rn, how far away does the normal force act from our new axis of rotation out here? Half the board away, so that's 2.5 meters times Fn equals Rb. That acts at the same spot, so that's also going to be 2.5 meters times the force of gravity on the board. That hasn't changed. That's still 300 newtons. Plus, remember, we solved for this force being 3.75 meters from the left edge. So that's 3.75 meters times 500 newtons. This simplifies to 2.5 Fn equals 2.5 times 300. That's 750. Plus 3.75 times 500. That is 1875. 1875 plus 750 is 2,625. I divide by 2.5. The normal force is 1050, just like we found before. So this is nice proof, or at least very strong evidence, that you can move the axis of rotation around when the object is not accelerating, when it's in rotational equilibrium, and you can figure out what the normal force is and everything works. okay, because we got the same answer doing a torque analysis as a forces analysis. Last question for the front. If a 500 Newton force were removed, if this 500 Newton force were removed, what is the angular acceleration of the seesaw? Note, the rotational inertia of the seesaw is I equals 250 kilograms times meters squared. We're not going to worry about the units, but those are the units of rotational equilibrium. Or excuse me, of moments of inertia or rotational inertia. So if we're going to remove this force, let's take the axis of rotation back to the actual pivot point. If an object is going to accelerate, okay, if it has angular acceleration, then the axis of rotation has to be where it actually is, right in here. So, going back to here, we know that the normal force and the force of gravity from the board are no longer providing torques, and there's no more force here, so that can't provide a torque. The net torque must be equal to simply the torque from the child sitting there. Remember, that's a counterclockwise torque, so that's going to be positive. T, or tau 1 equals I alpha. Let's see, we calculated tau 1 last time. We got that it was, and back when we had the axis of rotation over here, we know that the child is 2.5 from the axis of rotation, and we know that their weight is still 250. So this is going to be 625 Newton meters again. And if you're confused about how to calculate that, just look right up here. Equals 250 kilograms times meters squared times alpha. We solve for alpha. 625 divided by 250, and we get 2.5 radians per second squared. Okay, just like linear acceleration is meters per second squared, angular acceleration is going to be radians per second squared. That is the amount of acceleration right off the bat. Now that's going to change once this starts to tilt, and the force and R are going to become they're going to be at different angles. But the initial acceleration is this. Okay, we're not going to test anything past that. So our conclusion here, if in rotational equilibrium, you can set the axis of rotation to be anywhere. If you're not in rotational equilibrium, then the axis of rotation must be where the actual axis of rotation is. Okay, must be where it's actually rotating about. All right, we do have a few minutes. I'm going to get started on the next one just to make sure that we can save time and save you guys some videos and some questions here. Number 2. A lever is made out of a metal bar of mass 5 kilograms and length 1.5 meters. A worker is using the lever in order to push objects into the air and hold them steady by setting the object on a plate of negligible mass attached to one side of the bar at 0 meters and pushing down the other side at 1.5 meters. So let's just draw a picture of what this is. We've got a bar. Okay. It is pivoted, let's see. Okay, A says if the fulcrum, the pivot point, is in the middle of the bar, how hard must the worker push down the bar to support a 20 kilogram object? So, fulcrum right in the middle. There is a plate over here that holds an object. It's a 20 kilogram object. Actually, we're going to change the mass around, so we're not going to draw that in. And we want to know how hard the worker has to push here to support said object. Let's draw in our axis and our rotational axis. Counterclockwise is positive. Let's talk about the forces that are acting. Very similar to last time. There's a force downward over here. There's a force downward over here as well, but we know that it's the force of gravity on the object, so I'm going to do FGO. I know that from the pivot point there's a normal force upwards. We're going to call that FN. And I know that there is a force downwards because the board has some mass, therefore there's gravity on it. Downwards, this is FG, and what do we call it? FG from the board. There's your forces. If the fulcrum is in the middle of the bar, how hard must the worker push down on the bar to support the 20 kilogram object? Well, one of the forces that we don't know, just looking at them right now, we can calculate this very easy, we can calculate this very easy, and we're looking for how hard you have to push. So that's what we're looking for. We don't know the size of the normal force. So since we don't know the size of the normal force, it's a good idea for us right now to set our axis of rotation right here. And since we're looking for balance, we can set our axis of rotation anywhere, but this would be the smart place. Axis of rotation right in the middle. Since we put our axis of rotation at the middle, no torque from the normal force or the force of gravity on the board. So we're left with this. The net torque in this situation is going to be the torque from the object, which is counterclockwise, torque from the object, minus the torque from the worker's force. The worker's pushing down over here to support this, equals I alpha. We are supporting the object. We're not trying to cause a angular acceleration. This must be 0. Therefore, these two torques are equal to each other. So we have RO, FGO, sine theta O equals RF, F sine theta F. Now, because we're going to have to calculate the force of gravity on that object multiple times, I'm going to do it off to the side here so that we can always have it as a reference. The force of gravity in the object is equal to the object's mass multiplied by the acceleration due to gravity. Object's mass is 20 kilograms. Notice that's also going to appear in C and E. So 20 kg times 10 meters per second squared. FGO is 200 newtons. R0, or RO, is how far away the force is acting from the axis of rotation. The bar is 1.5 meters long. Since it's pivoted right in the middle, this must be 0.75 meters. 0.75 meters times 200 newtons. Notice that the displacement vector R to the left would be perpendicular to FGO even if they were lined up tail to tail. This must be 1. That's going to be the same thing over here. R is perpendicular to F, therefore this is 1. RF must be 0.75 meters because that's acting half the bar distance away, or half the bar's length away from the axis of rotation. Look at this. We have 0.75 times 200 equals 0.75 times F. Possibly kind of an obvious conclusion, but in this case, if it's pivoted right in the middle, you have to push down with exactly as much force as this weight pushes down on the bar. The force you need to balance this is 200 newtons. If the worker stands on his side of the bar to apply the force, how much mass can he support on the other side? Well, that means that we take the force and we change it to the force of gravity from the worker, which is just the mass of the worker times acceleration due to gravity, FGW, or maybe let's call it the force, equals, let's see, 85 kilograms times 10 meters per second squared. That force is now 850 newtons. And that's going to be the same for D and F. Let's do the net torque equation again. We haven't changed anything besides the size of this force, so we're going to go with the same equation. Tau O minus tau F equals I alpha. No rotational acceleration, so that is 0. RO F G O sine theta O equals RF F sine theta F. Again, we still have perpendicular forces and R's, so those are going to cancel to 1. We know that RO is 0.75 meters. We're looking for how much mass he can support on the other side, so now we're looking to see how big of a mass he can support. So MO times G equals 0.75 meters times 850 newtons. 0.75 MO times 10 meters per second squared, because that's the acceleration due to gravity. 0.75 times 850 is 637.5. Divide, let's see, 0.75 times 10 is 7.5. Let's divide 637.5 by 7.5. We get that the mass that can be supported is 85 kilograms, same as his mass. Okay, again, we use torque, we prove this answer. Seems pretty simple, but in the next questions we're going to move that pivot point around. We're going to move the fulcrum, and you will see that things are not going to be quite as easy, okay? Matter of fact, they can be kind of useful to us, but the analysis is a little bit trickier.